Back to Solomon's 13, chapter 11. We're going to do alcohols and ethers. This is video 1, which will go through the nomenclature and properties of alcohols. Again, this is just the first of 3 videos in the series. Okay, so let's talk about what we'll see in this chapter. This includes the structure, properties, and nomenclature of common alcohols and ethers, the key molecules that contain such groups as the OH and the ORO, or ROR, and the reactivity of alcohols, ethers, and especially the group known as an epoxide. It's going to have very unusual reactivities. So what we're going to see here is that in this naming of these, the hydroxyl group or the OH group is bonded to a sp3 hybridized carbon, okay? It must be an sp3. And they are classified by the type of carbon we have. So here we have a primary carbon. So we have a primary alcohol. Here we have a secondary carbon, so we have a secondary alcohol. And here we have a tertiary carbon, so we have a tertiary alcohol. And just like with alkyl halides, we have slight different reactivities with each of them, so we need to identify whether they are primary, secondary, or tertiary. Okay. So if we are to name these right here, this would be ethanol or propanol, and we have to name it because this is number 2 carbon, so that'd be 2-propanol. We also call that the isopropanol. And here we'd have 1, 2, 3 carbons here giving us propanol, so we have 2-methyl, 2-propanol. And we'll get into the more systematic naming as well as we go forward. Okay, so again, we have to have an alcohol, has to be the hydroxyl on an sp3 hybridized. That doesn't mean there can't be other functional groups. For example, in the case of this vinyl group here, if we are 1 CH2 off of that vinyl group, we have the allyl group. And remember in the last chapter, we had allylic bromination, which is bromination adjacent to that double bond. Well, here this would be an allylic alcohol, and it's called allyl alcohol. Now you can also do this with 1 CH2 off of an alkyne, and we would call that a propargyl alcohol. And so, or we would name it propinol. In the case of the ene, it would be propinol. But if we have like we've learned with other reactivity, this allyl position and this benzylic position are really, really reactive because of conjugation. And so when we have an OH on that benzylic carbon here, we call it a benzyl alcohol, Again, notice they all are attached to sp3 hybridized carbons, but they are adjacent to other functional groups that gives them additional reactivity. Okay, so when we have it attached directly to a benzene ring, that's an sp2 hybridized carbon, and we call those phenols. When we talked about acids and bases, we said phenols had greater acidity than regular alcohols because of conjugation. And phenols run right in between carboxylic acids and alcohols and water. So that additional acidity comes from that conjugation. And in the next few chapters, we're going to learn that they have special names for benzene rings with different functional groups on them. This one just happens to be phenol. Think of phenyl group plus alcohol, phenol, okay? And then we would name them for, because phenol is naming the group, that becomes our 1 position, 2 position, 3 position, 4 position. So we'd have 4-methyl phenol, or 1 position, 2 position, 3 position, giving us 3-chlorophenol. But again, the most important thing is that alcohol is on an sp2 hybridized carbon and is conjugated, therefore it has greater acidity. Okay, so let's talk about some common names for ethers. Okay, so the ether functionality, obviously we get rid of that OH bond, and so we don't have hydrogen bond anymore. We now have dipole-dipole interaction. But when we have the R group, OR group functionality here, we can name them for their common names by just what alkyl groups are attached to it. So in this case, we have an ethyl group and an ethyl group, so we can call this diethyl ether. Okay, and notice there's a gap right here. They don't string together because when you name common names, they're going to have basically what the alkyl groups were plus what it is. So you'd have ethyl alcohol, or in the case of this, you'd have diethyl ether. So here we'd have T-butyl methyl ether, so T-butyl methyl ether. And in the case of this is a vinyl group. And so we can use the di-tri-tetra naming functionality and call it divinyl ether. And then this one would be phenyl methyl ether. Sorry, that's ethyl. Haha. Phenyl ethyl ether. And so we'd actually put it in alphabetical order. So this would be ethyl, phenyl, ether. Okay. And the correct spellings are on the next slide. Okay, so it's ethyl phenyl ether and T-butyl, because we don't do the tert as part of the name. The butyl is the alphabetical name. So butyl methyl ether, again, in alphabetical order. Okay, so now let's talk about the IUPAC naming for alcohols. We're going to start with all of our same rules, but now our alcohol is our functional group. Okay, so we've identified our functional group. That means we have to find our longest chain that contains the OH group, okay, attached to it. And then you put the alcohol at the lowest number, okay? Now this is the highest priority group we have right now. Remember, we start with alkanes, then alkenes were higher, and then alkynes, and now alcohols are higher. So even if you have an ene, you're gonna have to name this enol or einol, okay? And so we'll drop the E at the end, stating it was a hydrocarbon, and put the OL on there, so it have the all name. So if we look at some common ones right here, we would just look at the parent name here. And so we have 1, 2, 3. So that'd be propanol, propanol. Because remember, it was propane, we drop the E and add the OL. But we still have to identify where the OH is, and it happens to be on the 2 carbon, no matter which way you number it. Okay, so that would be good. So now here we have 1, 2, 3, 4. So we have butane. But when we have more than one alcohol, we get to use the di, tri, and tetra functionality. So we can say diol, triol, or tetraol. In this case, we leave it as butane and put triol. But we're not done yet. We still have to identify them. And we get the lowest numbers if we go from this side, 1, 2, 3, instead of going from the other side, which would be 1, 2, 3, 4. So that's not the right numbering system. So we're going to go with the 1, 2, 3, 1, 2, 3 dash butane triol, all in one word. Again, all in one word with our IUPAC names. Okay, and there are those spelled out nice and neat. Now this alcohol has a common name too. Remember, we call that isopropyl group, the bunny ear group. Well, that's the isopropyl group, and so we would call the common name would be isopropyl alcohol. Okay, so again, remember, the OH has to be on the longest chain. Even though this chain right here would give us 8, we cannot use octa in our system, so we have to use the longest chain we see, which happens to be this one right here with the alcohol on it, which is 7. Okay, and then we have to number from this side to give the OH the lowest position. And so that's going to end up with our OH on 2. So we have 2 heptanol right here, 2 plus 7 carbons plus an alcohol. So that's where we have. And then the group here is 1, 2, 3 carbons. So we have 3 propanol. So see how all the other rules work. So we're just adding that rule that the OH has to be on the longest chain. It's exactly like if we had an alkene or an alkyne. All right. So now let's talk about some common names for ethers. Oh, we already talked about common names. These are the IUPAC names for ethers. So ethers are always substituents, just like alkyl halides. Okay. So alkyl halides, nitro groups, phenyl groups are always substituents. Okay, so what we have to do is we have to find the parent chain, which is the longest chain. In this case here, ethyl is our longest chain. So what we're going to call that is our parent is now ethane, because it is that. And then the ether is going to be our substituent. Now, to make the ether a substituent, we take the number of carbons we have and add the word oxy. So in the case of 1 would be meth, oxy. In the case of 2, it'd be eth-oxy. In the case of 3, it'd be prop-oxy, okay? And there's an error on the next slide, so make sure you write that down. So in this case here, this is our attached substituent, so we're going to call that eth-oxy. So we're going to locate it at 1 eth-oxy ethane, all in one word. Okay, now let's do the same thing for this one. The longest chain is bute, so we're going to use butane, butane, right here. And then we have a propyl group here, so we have to use prop-oxy. And it's on the 1 position again, so 1 prop-oxy butane, all one word, okay? Now please note the error on the slides, please fix that. All right, moving on to the next thing is the nomenclature of ethers. Now, when we have the nomenclature of ethers and their common names, we would say they would be like diethyl ether. But when we have cyclic ethers, we have actually special names. So in the case of the the smallest one we can make, which is 3-membered ring, we have cyclopropane, right? But we've replaced one of the carbons with oxygen. So in that case, we're going to call it oxacyclopropane. Okay. Occasionally, it's also called oxirane. Occasionally, it's called an ethylene oxide, and a lot of times it's just called an epoxy. So it actually has multiple names, and we're going to use a couple of those names would be oxirane, oxacyclopropane, and epoxy. Now, if we moved on to a 4-membered ring and we placed only one of the oxygens, we'd call it oxacyclobutane. And if we go to the next one with 5 in it here, we learned it as tetrahydrofuran when we were talking about our aprotic solvents, our polar aprotic solvents. But the IUPAC name is actually oxacyclopentane. So we've replaced one of the carbons with an oxygen there, and so we have oxacyclopropane. But we will more commonly use it as THF, or tetrahydrofuran. What if you replace 2 of the oxygens in the ring? Well, you have to say that you have 2 oxygens in the ring. So in this case here, we have one of the oxygen is going to be position 1, just like this would be position 1, 2, and 3, and 4, because the thing that's changing it is the oxa, so that's where number 1 starts. We're going to do a 1, 2, 3, and 4. So we have 1, 4 dash dioxacyclohexane. And so that name is actually shortened, and you can normally see it as 1,4-dioxane. Now this is the structure that's found in the dioxane pesticides that are been removed because they build up in the environment, but those are actually having benzene rings hooked to them here and here. So this material is not nearly as toxic or as bad for the environment as the dibenzo compounds, but we still have to be careful about how we use it. Okay, so let's talk about the physical property of alcohols and ethers. So when we had alkanes, all we had was induced dipole interactions. And the more surface area we have, the higher the boiling point. Okay, in the case of the diethyl ether here, we actually have a dipole, a net dipole here. And I'm going to show that we have a polar bond here going in this direction and a polar bond here going in this direction, which means we have a net dipole in this direction. So it can have dipole-dipole interaction. And those are stronger than van der Waals interactions. Okay, so but when we look at this here, we've lost some of the van der Waals interactions that we would get from having 2 of these. And so the boiling point really doesn't change that much by having that dipole-dipole interaction compared with the induced dipole. But look what happens when we have hydrogen bonding. The OH gives us hydrogen bonding, and the boiling point jumps up dramatically because of that. Because hydrogen bonding is the more higher energy interaction between them. It has a stronger bond than dipole-dipole, and dipole-dipole has a stronger bond than induced dipole. All right, so let's talk about the physical properties of them again. And so when we have alcohols, we think that, okay, that has an OH group on it, it's going to be soluble in water. Well, it turns out ethers, because of that dipole interaction, it can also be soluble in water because the ether can be hydrogen bonded to by water. The ether itself can't hydrogen bond, but it can be hydrogen bonded to by water. The alcohol can both hydrogen bond to water, and the water can hydrogen bond to it. Therefore, ethers actually have solubility similar to that of alcohols because of that dipole interaction, dipole hydrogen bonding interaction. The solubility of alcohol slowly decreases as the hydrocarbon portion or the alkyl portion gets longer and longer because it becomes more greasy, more alkane-like, and less of the available area is for hydrogen bonding. So how does that affect the properties? Well, if we look at the properties on the alcohols here, we see that our OH group here allows us to have a boiling point of 64 degrees. Remember, water, which is 18, and this is a little bit higher than just water. It's a carbon plus 2 hydrogens, so it's 14 higher than water, has a boiling point below that of water, because water can hydrogen bond twice. Okay, so just that one hydrogen bonding still allows it to happen. Now we have one hydrogen bonding, but we've increased the molecular weight, so that's the increase in the boiling point here. Again, increasing, these are about the same molecular weight, increasing the boiling point here. And as we get to this long chain here, that increases the boiling point, but it decreases the solubility. This right here is the solubility in water, and that means that if it's infinitely soluble in water, it means you can have anywhere from 0% methanol to 100% methanol in the water. 0% ethanol to 100% ethanol. It doesn't matter, it's all going to be completely soluble. But in the case of the hexyl here, it goes down to 0.6 grams per 100 milliliters, very low. And then by changing the shape of it a little bit, making it a little more compact, we get a little more solubility. Boiling point remains about the same. But what happens when you add two things that can hydrogen bond? So if we have the two OHs on a compound, it actually can make it infinitely soluble in water again, and it brings up the boiling point because you have two different hydrogen bonding sections. Okay, so the rule of thumb here is that for every 4 carbons you want to try to pull into water, you need 1 OH group. Okay, so let's look at ethers again. And so ethers don't have hydrogen bonding, but they do have increasing amounts of dipole-dipole interaction and van der Waals interaction. And so when we look at dimethyl ether here, that's a little bit bigger than water, but it doesn't have any hydrogen bonding. So its melting point is way lower than the melting point of water, and the boiling point's way lower because it doesn't have that hydrogen bonding, the strongest intermolecular interaction. By adding a little more mass, we actually get the boiling point to something reasonable at room temperature. And adding it to the diisopropyl, it adds more mass, and the dibutyl, adding an extra ether here. So now we have 2 dipole-dipole interactions, and that increases its boiling point. So if you go from 1 dipole-dipole, it increases the boiling point, to 2 dipoles, it increases the boiling point. If you go from 1 alcohol to 2 alcohols, it increases the interaction and increases the boiling point. When we go to oxirane, which is that, remember that's the 3-membered ring there, it boils just below room temperature. But tetrahydrofuran, which is a little bit bigger, gives us a nice reasonable boiling point of around 65 degrees C. Okay, so that's the end of the first video in this series, and we will pick up with the important alcohols in ethers in the next video.